My name is Morgan Roy, and I am an assistant editor for SEG Publications team. I am also the production editor for SEG Discovery, and that's our quarterly publication. I've been with SEG for about 4 years now, and I love every minute of it. So I'm happy to be here today helping host this webinar. For those of you who are not familiar with SEG, the Society of Economic Geologists, we're a professional society committed to advancing the science of geology through the scientific investigation of mineral deposits and mineral resources and the application of those to exploration, mineral resource appraisal, mining, and mineral extraction. This includes the providing of world-class publications, workshops, webinars, field trips, and conferences, as well as developing the next generation of successful economic geologists. We highly encourage anybody interested in our organization, especially students and early career professionals, to visit the Society's webpage for more information. Also, now is a great time to join SEG or renew your membership and take advantage of all that we have to offer. So you can scan this QR code here or visit segweb.org for more details on membership. Once again, welcome to the Brian J. Skinner and Waldemar Lindgren Lectures webinar. We're excited to be able to share two insightful presentations with you today, presented by the 2024 recipients of the SEG Brian J. Skinner and Waldemar Lindgren Awards. Each awardee will present a 45-minute lecture showcasing their innovative and widely recognized research in the field of economic geology, which will be followed by an in-depth Q&A session led by David Cooke, who is our editor for economic geology. For some greater context regarding the significance of these awards, the Brian J. Skinner Award is presented annually to the author or authors of an outstanding paper published in economic geology. The award recognizes the most innovative and original paper appearing in any of the 8 issues in a single volume of the journal. Papers are judged on technical excellence, innovation, and impact on the science of economic geology. While the Waldemar Lindgren Award is presented annually to an individual in recognition of research published within 8 years of their terminal degree that represents an outstanding contribution to economic geology. We are excited to have both of these award recipients here with us today. So just to go over our agenda a little bit, first I will introduce David Cooke, and he will speak a little bit on economic geology. And then we'll hear the first lecture from Bertrand Rottier. We'll have a Q&A, and then we'll hear a lecture from Federico Cernuschi, another Q&A, and then we'll have final comments and closing. Again, this is being recorded, and that recording should be available next week for on-demand streaming. All right, so first off, I'd like to introduce David Cooke. David is a professor and the director of the Center for Ore Deposits and Earth Sciences, or CODES, at the University of Tasmania. He is an internationally recognized leader in economic geology, having published 176 internationally circulated peer-reviewed papers and book chapters across numerous deposit types, including porphyry, copper, molybdenum, epithermal precious metal, and sediment-hosted zinc-lead deposits. His research integrates fieldwork, chemical modeling, mineralogy, fluid inclusions, isotopic studies, and microanalytical methods. He has a long history of research management, participation, and interaction with industry partners, as well as experience in knowledge transfer from academia to industry and student supervision. David has made many contributions to the Society of Economic Geologists, including his current position as editor of economic geology. David, I will turn it over to you.
Thank you, Morgan, and thank you so much for the invitation to be part of today's exciting session. Just a few words about economic geology. I'm wearing my hat as the editor of economic geology, the incoming editor. Economic geology is our society's major forum for the dissemination of new ideas, concepts, and insights regarding the world's premier mineral deposits. It's also where we communicate major developments regarding exciting new major mineral discoveries and also advances in exploration methods. The journal publishes manuscripts on all aspects of economic geology, including all classes of mineral deposits and tectonics, geochemistry, and geophysics of mineralized regions. We publish experimental studies, we publish sampling statistics, exploration techniques, and potential new source of metal. So there's a great diversity of topics that we try to cover, and we continue to grow those topics as our science evolves. So now we're seeing a lot more contributions on critical metals and on machine learning. So the journal continues to evolve as our science advances. Now, with regard to our science itself, it is really essential that we communicate effectively around the globe about these major new scientific advances. And we have an interesting challenge with our society in that we need to communicate to industry, to government, and to academia. So we're serving a greater sort of range of activities than many sciences do because we have such a strong professional aspect to our society. So our two speakers today are really great exemplars of the importance of effective scientific communication for the dissemination of their new ideas and their insights, and also how that effective communication, whether it be through peer-reviewed publication or oral presentation, is vital for their career development and for the raising of awareness across the society as to the big new advances we're making. So I hope you're going to enjoy today seeing both Bertrand and Federico's presentations because they really showcase what we're hoping to see in our brilliant young scientists coming through and advancing our society. Just a couple of facts and figures about economic geology. We publish around 80 manuscripts a year. Last year, there were about 300 manuscripts submitted to the journal. So you can see that we publish the best of the best that we get. Over that 300 manuscripts, last year, there were contributions from residents of 37 different countries. We would love to grow that geographic diversity, and we'd love to continue to grow the diversity of the science topic. So I hope all of you listening today might feel inspired and stimulated to consider whether you have a contribution that might be worth making to our society through a publication in economic geology or through our other forum, the SEG Discovery Forum. So please listen and learn today, enjoy the presentations, contribute to the Q&A, and I hope we meet you or hear from you at one of our society meetings and that you contribute to our publication forum. Thanks. Thanks, Morgan. Okay.
Okay. Thank you very much, David. All right. So I would now like to introduce Bertrand Rottier. He is a professor of metallurgy in the Department of Geology and Geological Engineering at Université Laval. His work focuses on the physico-chemical processes behind deposits of critical and strategic metals, like rare earth elements, graphite and copper, and gold, as well as the development of new exploration methods. Now his work is mostly located in various regions of the Quebec province. Bertrand received the 2019 Mineralium Deposita Best Paper Award from the Society of Applied Geology and the 2024 Waldemar Lindgren Award from the Society of Economic Geologists in recognition of his contributions to research in the field of economic geology. All right, I will hand it over to Bertrand.
Okay, so I will start to share my screen. Okay. Okay. Seems to work.
Yeah, looks good.
Okay, thank you. Okay, so hello everybody. So they asked me to give some word about me. So I am Bertrand Rottier. I'm currently associate professor at Université Laval. So I did my BSc and MSc degree mostly in France. So as you can see, I have a very strong French accent. I am very sorry for that, but I'm French. And then basically I did my PhD at the University of Geneva under the direction of Professor Louis von Botte and Dr. Klein Tusmanov on CO de Pasto porphyry rated epithermal base metal deposit. And then I moved to Germany in the BGI to work with Andreas Odeta on porphyry gold deposit located in Central Europe. And since 2019, I am now now professor at Laval University, on where I work on a lot of different topics, including orogenic gold deposit, graphite, rare earth element bearing like magmatic system, and also still a bit on porphyry deposit. So today I choose to to present you some work on the quartz texture and chemistry, and to see if they are good tracer for the mineralizing fluid evolution, mostly for porphyry system, and I will also do fluid degradation. So it's a work which have been done in association with a lot of different collaborators, including Vincent Casanova, which is currently research associate at Laval University, but also include a part of work which have been done with Kalin Tusmanov, with Funbote, Andreas Odeta, and also many others. So I will try to do not rush too much, and I will try to stick on time, and will try to be simple and also to go more in deeper detail in some subject. So first, what is quartz? So quartz is quite simple. It's SiO2 in terms of chemical composition, and what is very nice with quartz is it is common in and stable in a lot of different environments. So something that we often forget when we speak of quartz, also in porphyry system, is we have the transition from beta to alpha quartz at 573. And we have quartz that precipitate at higher temperatures than that in porphyry system. And it means that during cooling, they will go from the transition from beta to alpha quartz, which is associated with an expansion of the crystal structure and will create failure. I think Federico maybe will speak a bit of that, but just keep that in mind. Okay, what is quartz? Quartz, basically you have a tetrahedra of silicon and oxygen atoms. And generally, we have a low trace element concentration in quartz, which generally is few thousand of ppm. And as the chemical composition of quartz is very simple, we have just few possible substitutions. So it means that it's easy to identify elements that occur in the structure as inclusion in quartz. So the main substitution that we have in quartz is basically the substitution of a tetravalent cation with a silica cation. So it's a case of titanium, germanium, and tin, for example. What we can have also is the substitution of one of these silica cation with a tetravalent cation, like aluminium, which is a much common one, iron, boron, arsenic, gallium, but also antimony. If we do this kind of substitution, we have a charge which is unbalanced. That means that we need to incorporate an interstitial cation. So generally, this one will be 1+, and generally is hydrogen plus, so proton. Then we can have also lithium, sodium, copper, silver, and potassium. And this cation will be hosted in the central channel of the quartz structure and make it very easy to diffuse. So we can have very fast diffusion inside quartz. Just to show you some example, that is images of quartz which have been heated at 1000 degrees C for melting fusion purposes. I just want to show you this picture because I think it's amazing. Here you have the EPMA map of copper. And you can see that we have copper directly in the structure of the quartz, which correlate with the EPMA map of aluminium. So what's happened during heating is basically we replace the 1+ cation that was in the central channel of quartz by copper, just by having heating our sample. The source of the copper was the wire present in the stage. So why the take-home message of this picture is just to say, be careful. So the diffusion can affect the composition of your quartz, but it also affect more the composition of fluid and melting fusions. So it can be very important at temperature above 600 degrees C. So always be critical about your trace element content of quartz and also what you get from your silicate melting fusion and fluid inclusions. Okay, what is also very beautiful with quartz is we can do CL imaging. It's a very powerful tool to see the internal texture of quartz. As you can see, these kind of beautiful pictures. And we can do SEMCL images with an electronic microscope, or we can do also hot optical CL. If you are interested by that, you can see all the work of Thomas Manneke from Colorado School of Mine and collaborator. Other possibilities to do cold optical CL. That is less effective for quartz because generally the CL intensity is very light. But what is also very nice with CL is it is a function of the trace element content of quartz. And for quartz form at relatively high temperature. We'll have a titanium content above 10 ppm. And generally, in such case, we see a very good correlation between the titanium concentration of quartz and the CL intensity. Here is an example. Here in blue, you have the titanium content of quartz. And we see very well that the high titanium quartz has a very high CL intensity. And when we move to the low titanium quartz, we have a low CL intensity. I have another example from Federico Cernuschi, who will present just after. Is a beautiful example where you have a quartz from a B vein with different CL intensity. And then we have a lake quartz, which is lower in temperature, lower in CL. And we see that the titanium in quartz very well correlate with the CL intensity of quartz. So in porphyry system and for high temperature quartz is a very powerful tools. If we move to a epithermal system, is maybe less, the correlation with the CL intensity and trace element is really less evident. That is an example of Rottier from Casanova et al., which is an epithermal polymetallic deposit. And when you see beautiful CL zoning, and here you have the EPMA map of aluminium. So for example, for the first quartz, we see that we have a kind of negative correlation between CL intensity and aluminium. And here is also a second quartz from the same deposit, almost the same area. And we see that we have also beautiful oscillatory zoning, but in this time we have a good correlation with aluminium. So for epithermal quartz, a link between the CL intensity and the trace element and specific trace element concentration in quartz is difficult. Aluminium exhibits anything from partial correlation to anti-correlation with luminescence, whereas antimony seems to play a role in some quartz from its epithermal system, but we need more data to be sure of that. Okay, how we can date trace element of quartz? There is different methods that can be used, and all of them have advantages and disadvantages. So we can use EPMA, micropop. So generally, if you use a classical method, generally you will be able to detect very few elements because the limit of detection will be above few hundred of ppm. If you use a special method where you try to optimize your EPMA, generally you will be able to decrease the limit of detection up to 10 ppm more or less. So it's very nice to analyze specific element, but you will analyze generally one or two elements. What is good with this PMA, it's not showing this figure, is the I forgot the word. The spatial footprint of the EPMA is very small. It's like 1 to 5 micrometers, so you can analyze specific area of your quartz crystals. One other method can be SIMS. SIMS is very nice. You can analyze up to very low concentration, a limited list of elements. Generally, the spatial resolution is quite good. It's 15 to 10 micrometer, but it's very expensive and time consuming. Then we can use LAICPMS. It's very nice. It's cheap and fast. We have few problems with LAICPMS is the risk of explosion during the ablation of your quartz, and also the spatial resolution is relatively poor, and also you go very deep in the crystals. So this means what you have analyzed by LAICPMS is difficult to relate to the SEMCL images of your quartz. Okay. So if we move to porphyry system, I think most of you are very familiar with porphyry system. So porphyry system is a series of ore deposits which are generally formed along center of a porphyry plug in place in the upper crust. So close to the porphyry plug, we will have porphyry copper gold mineralization, and then around this plug, we can have different ore deposits like proximal skarn, distal skarn, high sulfidation epithermal gold silver deposit, or epithermal polymetallic deposit as vein in volcanic rock, for example, or as carbonate replacement ore bodies. As function of the depth of emplacement of your porphyry plug, you can have different vein generation. And so we have different vein generation in the porphyry system. I will not speak today of all of them. I will speak basically of few of them. I will speak of what I call bonded vein, E-type vein, B vein, C vein, D-type, and E vein. And I will go to each of one to describe their CL characteristic, and then we will discuss the trace element characteristic and with food equation. Okay, if we go to banded vein, they are very typical for shallow gold-only porphyry or gold-rich porphyry copper gold deposits. Generally, they are quite thin, from few millimeters to few centimeters, and they are characterized by the occurrence of these bands, dark bands, generally full of vapor, and also sometimes with magnetite inclusions. And generally, these bands are parallel to the wall of the vents. They are found at very high temperature, generally above 600 degrees C. And if we look in detail, often they are associated with salt melt inclusion or very weird silicate melt inclusion. I will not speak of them today. But I will also, in terms of CL texture, they show very beautiful CL texture with very well-formed quartz. So this is an example from Cerro de Pasco from Peru, and this is an example from Deva from Romania. So we see beautiful CL texture, well-zoned quartz, and also sometimes at the border of the vein, it's not obvious here, but we can see bothroidal texture, which probably records the fast precipitation of quartz in those veins. So that brings me to my first duration. I will try to be fast on the possible influence of the high temperature vein on the copper-gold ratio of porphyry copper-gold deposit. So why I want to speak of that is because, I mean, I think we have not explored enough this possibility. So when we look to the grade of porphyry deposit in terms of copper and gold, we see that we have a large range of gold grade in porphyry copper. Some of them are very gold rich, like for example, Baudelaire and Cerro Tazole, and have good grade of copper. Other are more what we call the gold only porphyry deposit, where good example will be, for example, Kisladat, which are quite rich in gold for porphyry and generally quite copper poor. So what I have done during my postdoc in Bayreuth in Germany, I have tried to find if we can have magmatic processes that can explain the low copper content of this gold-only porphyry deposit. And I mean, I have worked 2 years on that, and I have found no things that can explain why this porphyry have no copper. So then we go back to the vein to try if it is an hydrothermal process that can explain why this porphyry deposit have a very low copper and quite decent gold grade. So when we look to this banded vein, generally has high temperature quartz, and we have very few copper sulfide associated with the high temperature quartz in these high temperature veins. But if we look very in detail in the dark band, we have large vapor inclusion, magnetite, brine, but also we have very small bornite inclusion, as you can see here. They are small, but they are there everywhere. So basically, we were thinking of what is the possible influence of this small sulfide on the copper and gold grade of those porphyry. So why we were thinking that is because we know from former work, mostly Fraley and Friend 2014, that the gold solubility in bornite and also in chalcopyrite, here you have for bornite, here you have the graph for chalcopyrite, increase a lot with temperature. This means high temperature bornite can host a lot of gold up to few thousand ppm, and high temperature chalcopyrite can host also a significant amount of gold. So this idea was not new because Kessler et al. Have tried to test this idea in 2002, and basically they have analyzed sulfide from different gold-rich porphyry deposits, but it was quite disappointing because they never get gold grade above like 2 ppm. But what we have done is we have tried to analyze sulfide, bornite or chalcopyrite, fully encapsulated in the high temperature quartz that we found in this vein. And for Kralovae, a gold porphyry in Slovakia, we get gold content of bornite which were reaching up to several thousand of ppm. So it means that is quite gold rich. You can see the laser ablation signal here. For Deva, we've done the same. We have analyzed high temperature sulfide, which were present in the high temperature quartz, and also we have analyzed copper sulfide, chalcopyrite, and bornite that were present also in the vein, but associated with lower temperature quartz. And we get like gold content, which is lower than Kralovi, but still high, between few tenths of ppm of gold to few hundred of ppm in the high temperature in the sulfide, which are hosted in the high temperature quartz. But in the sulfide that was associated with low temperature quartz, we get very low gold value, basically similar with the finding of Kessler et al. So basically, what I think is indeed in porphyry gold deposits, this high temperature vein associated with high temperature precipitation of copper sulfide can explain the low copper gold ratio of this deposit. Why there is in gold-only porphyry deposit no copper is probably because the precipitation of chalcopyrite and bornite at lower temperature in the system are probably not efficient because they are too close to the surface. But the gold content of those deposits are probably related to the few but present high temperature sulfide. But it needs more studies. For that I share it with you. So I think we should spend more time to analyze those sulfide. Okay, I finished my first equation. I am back to the vein. So after the bonded vein, which type of vein we will discuss today is A-type vein. So A-type veins are generally thin and irregular, up to 1 centimeter. They are generally formed at high temperature, up to 700 degrees C. And if you look in detail in them, they are often rich in silicate and oxide inclusion, including rutile, biotite, pyroxene, actinolite, and feldspar. And there is also silicate metal inclusion in them. We'll come back to that later. Okay, in terms of CL imaging, it's very amazing. So CL imaging, the A-type vein are always something like that. So we see kind of unzoned quartz or always with blurry zonation. So that is an example from Cerro de Pasco. Here you have an example from Butte, same thing, no view zonation. Here is an example also from Butte, sorry. Here you have an example from El Teniente, almost no zonation, Bingham, almost no zonation, and also from Red Hills. Okay, why we have no zonation is a good question, and I don't really know is something that I'm asking myself. It is probably, can be diffusion. I don't think so, because the CL intensity is controlled by titanium in high temperature quartz, which is characterized by a low diffusion rate. It can be plastic deformation because these A veins are formed in a porphyry plate which is not totally solidified, but do not match with the fact that we see also this blurry zonation in A veins which are hosted in the adjacent host rock that was fully solidified. It can be linked to the beta to alpha quartz transition, but normally it should not. So it's an open question, but it's very typical of A vein, and it's very easy to differentiate A vein from B vein based on this CL characteristic. Okay, I have my second fast digression, will be very fast, and I have no more after that. When we look to this A vein, and we start to see silicate melt inclusion. So here is a picture of a silicate melt inclusion hosted in magnetic quartz, and for comparison, silicate melt inclusion hosted in hydrothermal quartz from E vein. So you can see they look like very similar. Okay, they are quite small, and it's probably for that that people have missed it, but we recognize them when we look to A vein, we can see them in a lot of porphyry systems. So if we analyze these silicate melt inclusions, generally we realize that they have a composition of the silicate melt. It's not a weird composition. They have a composition that corresponding to a highly evolved rhyolite. So that is, for example, an example from Cerro de Pasco again. The square is silicate melt inclusion in magmatic quartz, and the triangle is silicate melt inclusion in hydrothermal quartz. Here you have rubidium versus cesium, which both are good indicators for magmatic differentiation. So generally, the silicate melt inclusion are more evolved than the silicate melt inclusion that we find on the host intrusion. So it means that is even more evolved melt. So how it works, why we have silicate melt inclusion in the vein? So there was a first proposition by Stefano Vaita in 2014 from Elasticité, where they have recognized also the silicate melt inclusion. So they propose that they could represent droplet of silicate melt transport by the hydrothermal fluid. Another possibility is that we need to maybe to explore is the heat solution of the silicate melt phase directly from the hydrothermal fluid. It's difficult, but technically maybe it's possible. So then it is important for the formation of porphyry copper deposit. Basically, currently I think is probably not crucial, but it can give us important information of the residual melt in our porphyry plug before fluid degassing. So I think we should take more time to look at them. Okay, I finished my second digression and I go back to the vein. So B vein, generally a bit thicker, regular, formed also at high temperature, but generally we think below 600 degrees C. They are also often associated with magnetite, rutile, and generally sulfide, mostly chalcopyrite, sometimes pyrite, and they are often associated with potassic alteration. If we look to their CL characteristic, the difference with E vein is we will start to see beautiful oscillatory zoning. That is an example of elasticity from Stefano et al., an example from Esbjerg, same beautiful oscillatory zoning, an example from Redhill, an example from Cerro de Pasco, the Danube. Okay, we always see beautiful oscillatory zoning. Okay. Then we'll move to the next, which is probably the most debated, and Federico will speak of that just after, is the C vein. So what I call C vein is a vein which overprint earlier vein, forming vein filling rich in sulfide. Generally will be chalcopyrite, bornite, and pyrite. Generally, we have very few quartz, and they can be sometimes associated with a chloride sericite alteration. So for me, what I call C vein, at least in my compilation, will be this darker quartz reopening the vein and sometimes spatially associated with copper sulfide. As you can see here from Cerro de Pasco, also a beautiful example. Here is an example from Deva, which is also quite beautiful. So you have this lake quartz cross-cutting, the earlier version, the earlier stage of quartz, and we see very well that is cross-cutting it. Okay, another example from Batuiro, from Skira et al. 19, sorry, beautiful AB vein with very well zoned quartz high luminescence. And then we have this late low luminescence quartz, often as spatially associated with copper sulfide. Okay, my next vein generation will be the D vein, will be formed generally below 450. They are more thick and regular. Here you have an example from Gaspé copper in Quebec, and here you have an example from the Alta porphyry in Argentina. So generally they are associated with quartz sericite pyrite alteration. They are rich in pyrite and can contain significant amount of copper sulfide in some porphyry deposit. Okay, in terms of zoning, we see as the B vein beautiful oscillatory zoning, but in terms of CL intensity, generally is a bit lower. Okay, then my last family of vein will be the E and the epithermal vein. So the E vein will be epithermal veins that we find in telescope system, and epithermal vein will be veins that we find in porphyry-related polymetallic deposit, such as cordierite. Okay, generally they are associated or not with phyllic, argillic, and advanced argillic alteration, as you can see here from the Alta porphyry in Argentina. And also we can have very common open space. Here is an example from Gaspé copper again, where we have an E vein with beautiful open space. And this one also is a very big E vein. Generally, they can be rich in sulfide, and as function of the sulfidation state of the fluid, we can find different type of sulfide. It can be energite, chalcopyrite, sphalerite, and galena. Again, if we look to the CL characteristic of those quartz, generally they are well zoned with beautiful oscillatory zoning, but in terms of CL intensity, it will be lower than the B, D, and C type quartz. Okay, so all quartz from the different vein have distinct CL characteristic. So it means probably that they have different chemical composition. So what we can learn from their different chemical composition. To try to answer this question, we have done a compilation of the quartz composition from 21 porphyry copper gold moly deposit and epithermal deposit. epithermal polymetallic deposit. All quartz analyses have been reclassified according to their CL characteristic based on the vein types that I have presented to you earlier. Sorry. Okay, so I will show you quite a lot of those graphs where we have different color. It corresponds to different quartz type. So in blue is volcanic magmatic quartz, mostly from arc magma. In brown, we have the bonded quartz from the bonded vein. In dark red, we'll have E vein. In medium red, let's call it like that, we'll have E or B type vein. So basically, in our compilations, there was not enough information to classify them as E or B type. Here will be the B type veins, the B type quartz from B type veins. Here will be the C type, here will be the D, and here will be the E. So epithermal vein, telescope, and porphyry deposit. And here will be what I call epithermal quartz, so quartz from epithermal polymetallic deposit mostly. Also, there is also, just for comparison, I will not speak of them today, there is quartz from granite-related system, so mostly tin tungsten deposit, where we'll have quartz from granite, quartz from penmatite, quartz from gryzen, and quartz from veins. Okay, if we look to the tetravalent cation in all of these different veins, we see that aluminum is the most common tetravalent cation. So generally it's between around 100 ppm and 1000 ppm. We have not really variation as function of the vein type. Maybe we can see an increase towards the E type and the epithermal type quartz. Iron is very scattered, is also the limit of detection is generally quite high with LAICPMS. And we see in some vein relatively high value, maybe it's due to solid inclusions, even if we have taken a lot of care to filter our data with solid inclusion, but it's scattered. But then for the other tetravalent cation, boron is very low and is rarely detected. And when it's detected, it's generally below 10 ppm. Arsenic and antimony is often detected and generally is quite low. But we kind of see a tendency for both arsenic and antimony of an increase towards the E-type and epithermal vein. Gallium is very low, generally below 1 ppm. If we look to the monovalent cation, something that we can see is lithium generally is very low, so below 10 ppm. We have some higher value in E vein from telescope system. Probably it can be just something which is linked more to the locality of the quartz compositions that we have compiled than really something meaningful, I would say. Sodium, basically we see variation between 10 and 100 ppm increasing toward like the epithermal type quartz. Potassium is generally the highest, that is around 100 ppm or below. And then we have also monovalent cation like rubidium, cesium, and copper, which are generally very low. Here we have high value from the bonded vein and is probably due to diffusions. Okay. For the tetravalent cation, like titanium and germanium, so basically we see a very good correlation between the type of the vein and the titanium content. So basically, if we go from bonded vein to epithermal vein, we see a progressive decreasing of titanium, and we kind of see a progressive increasing of germanium. It's less evident than for titanium, but it's there, I would say. Okay, so if we look very fast some graph in terms of correlation, so for aluminium and lithium, we see kind of correlation is not perfect, but I will argue that is because we have different trend of correlation, so kind of different line, which probably reflect like the composition of the fluid. All the fluids that form this vein have not the same lithium content, and it's probably for that we don't have a single beautiful correlation. For the aluminium sodium, we can see that the correlation is bad. There is no correlation at all. And so it can maybe due to inclusions, fluid inclusions, but we have to do our maximum to filter the data set for inclusions. Why I'm thinking that is probably not due to inclusion is because we have quite a good correlation between aluminum and potassium, so which makes sense if potassium is incorporated in the structure of quartz. And generally, if we have analyzed the fluid inclusions rich in sodium in porphyry systems, generally will be also rich in potassium. So if the high sodium value here will be due to inclusion, generally it should also affect the correlation with potassium. So it's probably just true sodium content. Also, we kind of see a correlation between aluminum and antimony is very rough, but what we see also is we have a high antimony content in low temperature quartz, so E-type and epithermal vein, and the correlation between aluminum and germanium is very bad. Okay, but what is interesting with such compilation? So what we have done that is because such compilation allow to see general trend. And as the compilation that we have done, we have tried to compile quartz from where there was information about the temperature of precipitation, mostly based on fluid inclusion study. So with that, we can look to the reported temperature with the titanium, with the concentration of our element in quartz. So here, for example, is for titanium. So we see quite good correlation between the reported temperature and the titanium in quartz. So we see negative correlation. We can see two different trends. So I will argue that this trend reflects difference of pressure of formation of the quartz vein because those one are from deeper porphyries than those one. But if we look to the other element, for example, aluminum with versus the reported temperature, we do not see a good correlation between aluminum concentration of our quartz and the temperature of precipitation. Maybe we have an increase of aluminum in the lower temperature quartz, as we can see here, but overall it's not very good. For antimony, we do not really see a correlation, except that we have higher antimony in our lower temperature quartz, epithermal and E-type quartz. I will argue that is not a reflect of the temperature, but is more reflecting the nature of the fluids that precipitated those quartz, which have probably a more important component of magmatic vapor in them, either directly magmatic vapor or contracted magmatic vapor mixed with either meteoric fluid or other magmatic fluid, which will be explain that the fluid will be that precipitate those quartz are enriched in arsenic and antimony, and that probably is reflected in the composition of the quartz. For germanium, it's not great, but we see an increase of germanium with the decreasing of temperature. So if we plot like ratio like germanium versus titanium concentration, we have kind of a trend. It makes sense because titanium decrease with temperature, germanium tend to increase. So we can do this kind of ratio, and why this kind of ratio are relatively interesting because they can be used to differentiate basically the different quartz from this different vein type. So basically, if we use like germanium titanium versus aluminum titanium, we'll have the higher temperature quartz plotting on the left of the diagram, and we'll have the lower temperature quartz plotting on the right of the diagram. And we have quite a good differentiation between the different type of vein. We have overlap, but otherwise it's a quite good discrimination. Okay, what we can do with such compilation is also to test the efficiency of discrimination diagram which have been proposed. That is one from Rust et al. 2012, if I remember well. So we can see that, I mean, for porphyry type quartz, for vein from E and B, sorry, I start again. For quartz from E and B type veins, it worked very well. They plot very well on the porphyry field. But then if we go to lower temperature vein like D and E, we are neither in the porphyry type field or in the epithermal field, and we have an overlap on the orogenic gold field. And also, if we look just from quartz from porphyry for granite-related system, we have also an overlap with the porphyry type quartz. So be careful with such type of diagram. There was another discrimination diagram which have been proposed in 1988, and which was based on a ternary diagram of titanium, 10 times germanium, and aluminum divided by 50. And when we plot our data from our compilation, we see very well that it does not work, but it's a very old diagram, and I think they have done their best with the data that they have at those time. Okay. So also what is very interesting with such kind of compilation is allow us to test the efficiency of the titanium in quartz thermobarometer. So this efficiency is debated. Why? Because we have some experiments that show an effect of the crystallization rate on the titanium incorporation of quartz. So it means that the titanium incorporation of quartz is not only related to temperature and pressure, but is probably also related to the speed of crystallization of your quartz, which makes it very problematic. So the point why it's debated is there is several equations that exist, and to be honest, there is new one which are published almost every year now. So it means which one is the good one, and it's not easy for, classical reader to understand which one is the best. Normally, it requires a knowledge of the titanium activity of your hydrothermal fluid. I would say that is less critical for porphyry system because, at least from my experience, when I look in detail in my different vent type, I always find rutile. If it's not rutile, I'll find anatas. So generally, I think we can be quite confident on the titanium activity for porphyry system, but it's really not the case for granite-related tin tungsten deposit, for example. And we have also another problem. In some vein, quartz from the same apparent generation can have titanium concentrations that can vary of tens of ppm without evident reason, meaning without evident evidence of variation of temperature. So it is really a good recorder of the temperature of precipitation of quartz is a good question. So we test the efficiency of different equations. We have tested the one published by Waldemar Lindgren in 2012, Seng et al. 2020, and Thomas et al. 2010. And basically what we see is generally we have a good match, I would say, but qualitatively. So indeed, if we compare the reported temperature with the calculated temperature with the thermometer of Waldemar data, generally we have an overestimation of plus 100 degrees C. But we have other equations that seems to match well the lower temperature one, others that match well the medium temperature one. But what we see is we need to be prudent. So another approach can be to use multiple thermobarometer. So it's something that we have done in 2018 in Porphyry event from Cerro de Pasco. We have tried to use rutile and titanite, so the zirconium content of rutile and titanite that were included in quartz. And basically, we find a mismatch between this thermometer of almost 100 degrees C or even worse. But to be honest, I don't know which one to believe. So I don't know if the zirconium in rutile is really more accurate than the titanium in quartz. And sometimes we get like higher temperature from the rutile, and sometimes we get higher temperature from quartz. So it's not easy to really know which one is the most accurate. Okay, so the take-home message is the accuracy of the titanium in quartz thermobarometer for hydrothermal quartz is difficult to assess. But if you want my opinion, it's probably not better than plus or minus 100 degrees C. So my take-home message will be to do not use it, to do not use the titanium in quartz isoplate with fluid inclusion isocore to calculate the temperature and pressure of formation of your porphyry events. Okay. So something which is also very common is to link the aluminum concentration in quartz with the pH or the CO2 content of the hydrothermal fluid. Why? It's because there is an effect on the aluminum solubility of the fluid, of the pH and the CO2 content. And that was basically from a work of Rottier et al. 2008 that shows that solubility of aluminum in the fluid at 200 degrees C in a porphyry system is much higher than at 500 degrees C, because basically the pH is much lower at 200 degrees C. And I think he's right. So if we look to our compilation, generally quartz which are formed at lower temperature, higher aluminum that was from higher temperature veins, but it's not continuous. And also what is very important is the mechanism of aluminum incorporation in hydrothermal quartz. And so also the aluminum content of hydrothermal fluid are not well understood. So maybe the fact that lower temperature quartz have higher aluminum in general is maybe due to an higher solubility of aluminum in the fluid, maybe due to the lower pH, but it should not be used as a direct indicator of pH in a way that if you see an increase of an aluminum in your quartz, doesn't mean that you have a decrease of pH. A good example from that is here you have the aluminum content for E and B type vents, and here you have the aluminum content of D-type vents, where we know that we have a decrease of pH from E, B to D type, and we do not see any variation of the aluminum content, nothing which is very obvious. So I suggest to be very careful when you use this correlation, and doesn't mean that's it. Be careful. Okay, and if we look for epithermal quartz, also in epithermal quartz, we can see, so here is an example from Cerro de Pasco. Here there is the oxygen isotope. I will maybe go to that after if we go there, if we have time. But in hydrothermal quartz from epithermal environment, you can see very fast and very sharp transition of aluminum content, which is indicated here by the yellow bar, and going from few hundred ppm to almost 1,500 ppm in this case. So very fast and transient variation of the aluminum concentration. And if we look to the vents and where we have found this quartz, we have no indication of any mechanism suggesting pH variation. Also, here is also an example from Cerro de Pasco, where we have quartz, which is from a quartz energized alunite vein, and is where in Cerro de Pasco we record the lowest aluminum content. And also in this specific sample, here in this crack, which have an aluminum content of 88 ppm, we have also alunite and carolinite inclusions, meaning that the feed was relatively acidic, but we have a very low aluminum content of our quartz. So just take a message, be careful with the correlation between your aluminum concentration of your quartz and basically the pH of your fluid. So can we do more with quartz? Yes, we can do in situ oxygen isotope to track fluid evolution, but I still have only 3 minutes, so I will maybe skip that just to show you very fast. A lot of work have been done on porphyry vents, and generally when we do in situ oxygen isotope in porphyry vents, we have like very constant value. So here is an example from an E vein, again E vein, again B vein, where if you analyze quartz from the same generation, you get very constant value. If you analyze quartz from another generation, you will have variation. An example also from Cerro de Pasco, very fast, where we analyze this quartz from banded vein. So if we look to the oxygen isotope composition, very constant. And if we move to another quartz generation, we have shift, but also very constant. Also an example from Federico, again, same thing. One quartz generation, very constant isotopic composition. We move to another quartz generation, very constant isotopic generation. Okay, Electricité, same thing. Also from Toulon in China, same thing. So basically in porphyry vein, oxygen isotope composition of quartz are generally constant in a single generation. And when there is variation, they are sharp, and there is a record fluid cooling and mixing with meteorite water. And generally, the meteorite water incursion occurs at the end of the life of the hydrothermal system and of an hydrothermal pulses. Okay, in some porphyry veins, the C quartz vein, record volumetrically minor incursion of meteorite water and are spatially associated with copper sulfide precipitation, but we'll let Federico to discuss that in more detail. Okay, I have no time to present the oxygen isotope value in hydrothermal quartz. I will just show you one beautiful pictures. Maybe let's say this one. If you are in an hydrothermal environment, it's totally different. Generally, we can see sharp and fast variation of the oxygen isotope in our hydrothermal quartz. And if you want to understand the story, to explain how it's possible to explain that, it will be another presentation. Okay, so conclusion. So CL imaging of porphyry vein are necessary to identify the different quartz generation occurring in a single vein. Trace element concentration in quartz show gradual evolution from E to E veins. Titanium in quartz is a good proxy for temperature, but should be used cautious. Is more a qualitative indicator than a quantitative indicator. Aluminium in quartz as proxy of hydrothermal fluid pH is suspicious and require more experimental work. And in situ oxygen isotopic analysis of quartz relays the dynamic and complex evolution of hydrothermal system. And germanium and antimony concentration in quartz are probably very good proxy for the germanium and antimony content of hydrothermal fluid. Thank you, and sorry for the few extra minutes.
All right. Thank you, Bertrand. All right, I can share my screen again here, just 1 minute. And we're going to begin a Q&A session. So anybody who has questions, if you want to go ahead and put your questions in the Q&A at either the top or bottom of your screen. All right. Let's pull up my slide here. There we go. Everyone should see it in a minute if you don't already. Okay, and I'd like to invite David and Federico to come on camera to participate in the Q&A.
Thank you, Morgan. And thank you, Bertrand, for a superb presentation. That was a really illuminating deep dive into quartz chemistry and thermometric analysis of quartz from a variety of techniques. We're starting to get a series of questions populating into the Q&A, so I hope you're happy to take these on board. The first one's from Vic Chevillon, who has asked, with regard the banded veins, are you seeing measurable effects in your small-scale traverses across banded veins, especially when you're going across transition zones between vein types?
I mean, yeah, so I try to find the question again. So basically, the question is for banded vein if we see variation in trace element in a transect. Basically, yeah, generally, so banded quartz vein are characterized by strong variation in titanium concentration. So basically, we can have titanium concentrations that will vary from, let's say, 100 ppm up to 400 ppm, and that is probably due to the speed of crystallization of the quartz, because it's vein where the quartz will precipitate very fast. And then when you have like later opening, yes, you see like this later opening have a different composition. But in terms of from the center to the border, I have not seen any systematic variation in terms of composition.
That's great, thank you. We've got another question from Sarah Bowie, who is saying really interesting correlations, but Sarah's wondering how the exact temperatures of the veins are measured. So yeah. You've already questioned the titanium and quartz geothermometer. What is your preferred workflow for working out exactly what the temperature of formation is?
Yeah, I think it's a very good question, and it's also the maybe the weakness of this comparison, because basically I use data from fluid inclusions to say that fluid inclusions are probably kind of good records of the temperature precipitation of quartz, and we can discuss that. But then I also, what maybe you have seen the error bar, which were very large. So we take like very I would say conservative assumption about the temperature of precipitation, and we compare that also with all the data from the same quartz generation in from each deposit. So it's very rough comparison just to see if it matches or not. So basically, if it doesn't match with this kind of rough comparison, it means that we should be careful. Is that so? It doesn't match globally, so it will not match perfectly. I mean, if you go to detail. So then, what is the best to calculate the temperature of our vein? I mean, it's a good question. Field inclusion, I think, from my point of view, will be the best, and then also the question why we need to have an exact temperature. I will say that we know that events are from 500 degrees C, maybe up to 700 degrees. We know that P events are from at lower temperature, but why it's really the utility to know that my B event is from my 500 degrees 30. And also it is realistic because my B event is probably from along a span of temperature, maybe not of 300 degrees C, but maybe of 50, 100 degrees C. So I think, I mean, most of the people in the past have already give like the temperature evolution of those veins in a qualitative way, and it's probably good enough for most of our application, I would say.
Great. Thank you for that, Bertrand. Hugo Carrasco is asking us whether there's any difference in the chemistry and the quartz temperature from the early quartz veins relative to the quartz that's precipitated with the sulfides in the C veins.
Yeah, so we see that with, yeah, maybe it was too fast, but yeah, we see that the CL characteristic is different. So the CL reflects the chemical composition. So generally the quartz, which is associated with the sulfide, have lower titanium content, and basically the main difference. Let me check. I think it's mostly titanium. Yeah, the most of use is really titanium, which is lower in C-type vein, and generally they are characterized by a bit enrichment in aluminum, but it's not systematic and it's probably not relevant. So it's really titanium.
Yeah, great. We have an anonymous attendee asking, have you looked at early halo or EDM veins in your study, or do you just not find enough quartz to be able to do the same that you've done with the other vein types?
I mean, it was a compilation. Myself, I never analyzed them, and because I never worked on porphyry deposit where they were very present. And nobody have analyzed them, but Federico, I don't know, maybe will show that there is quartz associated with those veins, and maybe it will be interesting to analyze them.
Yeah, we have done a little bit of analysis in early halos quartz, and it's also problematic because some of the quartz that we thought it was part of the early halo are actually overprinted A veins that are within the halo. But if you can assay the little bit of quartz that it's intergrown with the other silicates, you get very similar results to A vein quartz. So yeah, but we don't have much data.
All right. Thank you both of you for those answers. Max Hole's asking, is there a correlation between the oxygenating values and the titanium content of quartz? And shouldn't the lower temperatures be affecting the fractionation of the oxygen isotopes more strongly as you get to lower temperatures?
Okay, so there is two questions. First, so for the oxygen activity on the titanium in quartz, no, it should not, because the titanium titanium solubility of the fish should not strongly be affected by the oxygen fluidity of the fluid, and also, I mean, the incorporation of titan as titan is 4+ will not be affected by oxygen fluidity. So I have never think about that, but I think it should not.
Right. I don't think he was asking oxygen fugacity. He was asking about oxygen isotopes. So the fractionation on the oxygen isotopes is a strongly temperature-dependent fractionation.
Yeah, exactly. So basically, it's what we see in porphyry events. So sometimes we see, I went too fast with that, but sometimes we see like variation of few per mil, like from like kind of the early high temperature quartz from the C quartz associated with the sulfide, but that is mostly linked to the temperature of precipitation of the quartz. When we recalculate back, sometimes we have a bit lower oxygen isotopic signature for hydrothermal fluid, but generally is almost in the uncertainty of what we have calculated for the earlier event. When it's not, and it's not in the uncertainty, it's really lower than the oxygen composition of the hydrothermal fluid that have formed the earlier. Then, generally, we can explain it by just a bit of mixing with meteoric water. Generally, very few, up to 10-15% of meteoric water is enough to explain this shift of oxygen isotopic signature of the hydrothermal fluid forming this lake quartz. It's fine. It was a question.
That's great. Thank you. Leo Bonapartis has asked about substitution of tin into quartz. It seems to be quite limited, even though they have similar valences in +4 state. Do you know of a reason for that?
I would say that I have a reason why there is very few value on that. Is because tin generally is with other elements is very problematic by LAICPMS system in quartz. So, tin, phosphorus, calcium are very difficult to analyze accurately. Sometimes we have pollution, which is from either the cell or from the tube that affects the tin analysis in LAICPMS. So basically, in our compilation, there was kind of very erratic value, and we have discarded them, basically. So we have a quality problem on the tin analysis in hydrothermal quartz. So I cannot answer the question, but normally it should go.
Okay. Yeah, all right. Thank you for that. Carl Bino has asked, he said, well, great talk, Bertrand. Are there opportunities to utilize diffusion modeling across some of the sharp compositional boundaries that you've identified in the vein quartz to get at timescales broadly? If so, is there a particular geochemical or isotopic tracer that you think would be the best to use for this work based on the analytical limitations you mentioned?
I think there is already great paper which have published on that. Federico has done one about oxygen diffusion in quartz in the geology paper. Celeste Mercer that got the Brian Skinner Award in 2015 or 16 have done that for titanium in quartz. So then we can always argue which models they have used or not. But yes, so it can be you can use a quartz composition to do diffusion modeling and to get like information about the timing.
Great. Yeah, that's a great paper by Celeste. It's well worth chasing if you haven't seen it. Look, then we've got Syed Bagban is saying, it was a wonderful presentation. Unfortunately, I missed the first part. Could you just go back over which of the cathode luminescence methods you would prefer for quartz in general, cold or hot?
Okay. So me, I would say that SEMCL is the best first. Because we see much more the variation, mostly for low temperature quartz. Then if you want to do optical CL, which are probably also very interesting because with the different colors that you can see, you can have more information about the trace element. You need to do hot, I would say, because especially if you want to image low temperature quartz, hot optical CL give very beautiful result. And if you are interested to know more about that, I strongly suggest you to read the paper of Thomas Moneke from Colorado School of Mine and all the collaborators. They have done a very beautiful work on the CL the optical CL, the hot optical CL texture of quartz from a variety of deposits.
Great, thank you. We have another anonymous question. Do you see a trend in lithium concentrations through the paragenesis of the different porphyry vein types?
No.
Yeah, simple answer. And then Susan Dryberg has asked, do the correlations between vein generations and trace element chemistry get stronger or weaker if you look at the data set from a single deposit instead of the compilation across deposits? Is the relationship deposit specific?
Maybe for some elements it will be, yes. For example, for lithium, you will see probably maybe a correlation at the scale of the deposit. For other trace elements like germanium, antimony, and arsenic, as they are probably reflecting more the composition of the hydrothermal fluid than processes, I guess you can see much better the difference. In terms of titanium and aluminum, I think it will be always the same kind of trend. It's
Yep.
what I think is what we have seen. But for some element, yes, and there are papers that have already tried to do that. I think the paper of Medegan on the altar porphyry has done that. And there is a lot of papers in the, I would say, like few years, the last 2 years, that have published quartz concentration. So I think we'll have a better view in few years, because there is a lot of paper on quartz composition now that came out.
Excellent. Jocelyn Pelletier has asked the question about, have you been able to see any zonation of textures and compositions around porphyry copper deposits that might relate to the thermal aureole, the distribution of copper, especially with regard to the A-type veins? Do you see more copper proximal, distal? Have we got data sets robust enough to let us actually address that question yet?
No, I mean, my data set is not enough to check for that. I think it will be interesting to check, but yeah, I cannot answer.
Right. So I've got a question for you about potassium content in quartz. Micro-inclusions and fluid inclusions, how impactful are they on the potassium concentration? How do you go at filtering out those contamination issues to get at the true potassium content?
Yeah, it's a very good question. So first, I mean, what is nice in quartz, so you see the quartz, so you can filter for even before the analysis for big inclusions generally. Then what is nice, if you analyze the fluid inclusions, fluid inclusion in porphyry system have always sodium and potassium. So you can check first your concentration between sodium and potassium. We have done it, there was not great correlation between the two. So basically, it's a very good example of to check very fast, because the aluminum concentration in fluid inclusion is also very low. So basically, fluid inclusion pollution should increase the sodium and potassium without increase the aluminum. Then you can have inclusion of silicate, which is quite easy also to see, because I mean they will evolve in a single direction. Generally, where you will have potassium aluminum, but they will follow a specific ratio. So generally, I mean, if you do it carefully, it's quite easy to kind of discriminate the kind of the most obvious pollution. Then very tiny fluid inclusions or very tiny solid inclusion. I mean, normally you maybe there is some pollution, you cannot avoid them, yeah. But basically we have done our best, and for fluid inclusion, I would say from our compilation, the lack of correlation between sodium and aluminum versus that we have a correlation between potassium and aluminum is a strong indication that potassium is in the structure of the quartz versus sodium is not.
Great, thank you, Bertrand. I can see Morgan is back online, so Morgan.
I am, yes. We need to be wrapping up shortly here, but I think we have time for one more question, and I think I saw one pop up just now in the Q&A.
Yes, we did. So one more from an anonymous attendee. Is it okay if we use the same vein classification for the porphyry deposits, the A to E type veins, in veins associated with granite-related ore deposits related to grisons and the like? Is there any suggestions on that? And has anyone put out a paper that's suggesting vein types in granite-related tin tungsten systems, for example?
So yeah, the same we cannot use the same classification because this classification is typical for porphyry. And then, I mean, the chemical composition of vein associated to granite-related ore deposit have already been well covered by several publications. I don't have the name in my mind, but you can look in my 2020 paper, 2021 maybe, on quartz composition. I cite them, and some have done a very beautiful work, and they see very well zonation and composition. But for the titanium concentration, what we see from the compilation is not as simple than for porphyry. And why that is probably because the correlation for the titanium activity is much more difficult for this type of vein. Mostly for this type of system, mostly if you analyze quartz from pegmatite, quartz from grazen, for them it's very important to fit the titanium activity in order to have a kind of coherent evolution. At least try to understand qualitatively what's mean your variation of titanium content of your quartz.
Right. Thank you, Bertrand. Morgan, over to you.
All right. Thank you again, Bertrand, for that presentation and for that great Q&A session. Thank you to everyone who submitted questions. That was great. I move my slides here. There we go. Okay, I would now like to introduce Federico Cernuschi. Federico is an independent consultant specializing in the geology and geochemistry of magmatic and hydrothermal processes with a focus on porphyry deposits. He integrates classic hand lens observations and anaconda-style mapping with trace element geochemistry, spectroscopy, and other analytical techniques. Federico provides continued support to First Quantum Minerals and services to companies like Rio Tinto, Fortescue, and several juniors. In these roles, he has worked on exploration projects of varied geology and age across more than 20 countries and has provided training to multiple global exploration teams. His education includes the University of the Republic in Uruguay and Oregon State University. Federico is the 2024 recipient of the Society of Economic Geologists Brian J. Skinner Award. So I will turn it over to you, Federico.
All right, thank you. Gonna share my screen here. All right, is that good?
Yeah, that looks great, Fed.
Great, thank you. So thank you for the introduction. So a little bit about myself. I'm from Uruguay in South America. I study here first and work a little bit in exploration, mostly organic gold. Then I moved to Oregon. I was very lucky to study with John Dilles, did my master's and my PhD there. And also got to work a lot with Scott Haley. So after that, I've been working as a consultant in mostly in porphyry space, either related with the geochemical side of things or the geological side of things in mapping and making cross sections and making observations on rocks. So today I'm going to be talking about the timing of hydrothermal alteration and veining and the relationship with copper and moly and gold mineralization in porphyry deposits, and trying to reconcile what we can see as exploration geologists. That's what I do, using a hand lens and doing core logging and mapping, and how we can reconcile those observations with microanalysis. So I have a long list of contributors there. I'm going to mention a few, especially John Dilles, Jaime Osorio, John Prophet, and Kalin Kuzmanov, who are co-authors in this paper that was published last year in Economic Geology. And also I need to thank First Quantum, who sponsored this research when it started during my PhD more than 10 years ago, and also through our consulting relationship. So the question I'm going to be focusing today is, when is copper introduced and precipitated in porphyries? And we can frame this question in two different hypotheses. So the first one comes from more the field side of things, and is the maybe more traditional one, and it comes from the observation of these typical porphyry veins called A veins that are very early in the paragenesis of porphyries. And they have a typical sugary or apletic texture in the quartz. They have disseminated sulfide in the veins and also in the intermediate wall rock. And that's associated with hydrothermal K-feldspar and hydrothermal biotite. And if you look at a phase diagram like this one, that's an assemblage that we can infer relatively high temperature. So this kind of observation led to the idea that copper is introduced with these veins at high temperature instability with K-silicate alteration. And if you need to put a round number to that, it has to happen about 450 degrees Celsius. And this comes to what Bertrand was discussing on how can you measure this temperature accurately. And it's not really important it's 450 or 470. It's just a round number to sort of think about the problem. More recently, when we start doing cathodoluminescence in quartz veins, and Bertrand showed several beautiful images of this. And if you have a look in cathodoluminescence of a quartz vein like this one, you see that in reality, there are multiple generations of quartz in that vein. And this comes from early work from Patrick Redmond and Brian Rusk and Mike Reed. And if you see these sulfides that are disseminated within the A vein quartz, they are in many, many cases, or basically in every porphyry that has been seen with this technique, these sulfides in the A vein are in contact with a late generation of quartz that is dark in Cl or dull and cross-cuts the A vein quartz. And if you do different estimates of temperature in that quartz with fluid inclusions or titanium quartz, you get low temperatures. And to put a round number, below 450 degrees Celsius and as low as 300 or even lower. So this suggests that maybe the potassic alteration and the A veins were formed there first, and then the sulfides are introduced later with this later and lower temperature quartz. And that gained more traction with more recent work as studying these C veinlets or pain veins, which are not only cross-cutting A veins, but sometimes you can observe them on their own. And that also led to the idea that and they have this low temperature quartz, so that led to the idea that everything is introduced late and at low temperature. So to discuss this, we need to understand different vein types in porphyries. And I'm going to start by talking about two types of porphyries. There are many ways of differentiating families or subgroups of porphyries. We're going to talk about this in terms of depths of formation or emplacement. This is after the work done by John Prophet. You can see this is a cartoon from Yerington. You have a precursor batholith, and one of the cupulas that it's shallower in the paleocrust has all these dikes and leads to the deposit known as the Yerington mine. That's what we know as a shallowly emplaced porphyry and called A vein type porphyry, because the ore, in despite of what's introduced in the copper, it's related in space with the occurrence of A veins. And this is a picture from Batu Hijau in Indonesia, which is also an A vein type porphyry. And you see the sugary texture, disseminated sulfide relationship with K-silicate alteration, and they're biotite rich and magnetite rich. And from the same precursor batholith, you have another cupula, a bit deeper, and also deeper in the crust, another deposit called N. Mason Pass, which is what we call a deep porphyry or an early halo type porphyry. And that's because the copper ore is related in space with these alteration selvages called early halos rather than with A veins. There's not too many A veins in there. There's also K-silicate or potassic alteration, but there's biotite with muscovite inside the halos, and magnetite is virtually absent. Could be a little bit, but not too much. And this is an example from Jaquira, Peru, what we call an EDM halo. So this is important because both type of porphyries are pretty common, right? A vein type porphyries are probably the best known ones. They have been better described in the literature. You see a lot of A veins are very abundant in the ore. They have truncation by different porphyry dikes, and early halos, now that more people are recognizing them, they are there, but they're not very abundant. And we mentioned Batu Hijau, Yerington, but also El Salvador, Chucarupeki in Serbia, or even Jebelo here, which is a pretty old deposit in Sudan. And we think all these deposits form at some point, some depth that it's shallower than 5 kilometers. Then we have the early halo type deposits. Early halo types, little bit of quartz veins. So it's the opposite. Early halos are abundant and A veins are rare, but they are present there too. So it's a continuum between these deposits. We have Butte being one of the best examples, and Mason Pass, as we said, Hakira in Peru, Los Pelambres in Chile, Pribrezhny in Kazakhstan, and even Haib, really old deposit in Namibia. And then we have some deposits that have characteristics of both, where there's some areas of the deposit where early halos are more abundant than A veins and vice versa. Bingham and Encuentro being that, and I think this class, it's gonna get a bit bigger with some time. So both type of porphyry deposits, they share characteristics in the timing of veining and the vein types that you have in there. So this is after Gustafson and Hunt, the nomenclature of veinings. And the important thing here is the timing, right? It's what vein crosscut which vein. So we start with A veins. The Bertrand was showing many examples of all these veins. You have this sugary aplitic texture. They are discontinuous, very irregular, sinuous, and you have disseminated sulfides. And then these are crosscut by B veins, which are more straight-walled. They have the oscillatory banding in CL imaging, and sometimes they have continuous center lines of copper sulfides too. Both of these stable with potassic alteration, and they have copper. At some point where potassic alteration ends, we start having those C veins or paint veins, where there's little quartz and there is some copper sulfide and some characteristics of going into chlorite and sericite alteration. And when sericitic alteration is well established, we have the very typical porphyry D veins, which have a straight pyrite center line and alteration selvages with abundant muscovite. Early halos, they fit in this picture at the same timing as A veins. Here's an example of an A vein cross-cutting and displacing an early halo, and sometimes we see the opposite relationship even in the same deposit, where you can observe both vein and halo types. And it's really difficult to know timing when it's a vein and a halo that cross-cut each other. Early halos, they've been described for a really long time. Actually, before Gustafson and Hunt put that name and nomenclature on veins, these were described by Chuck Mayer for Butte. And there has been some confusion with D veins and the sericitic halos in D vein. And that's because these are the only two types of alteration selvages without a quartz vein inside. And we'll discuss this a little bit. There are many other names that have been used for early halos before, including EDMs, green mica halo, type 4 halos at Los Pelambres. Even Gustafson and Hunt in El Salvador, they recognize this Andalusite corundum alteration. Sericita verde, very common name in South America. And we're also going to bring into the discussion of timing of veins, other vein generations of quartz, because not all the porphyry veins with quartz are A or B. We have deep quartz veins that are typically barren and predate A veins, more related to USTs and massive quartz. Banded molybdenite quartz veins that postdate A veins and predate B veins, and they have moly but no copper. And some deposits have another moly generation with quartz after B veins. So we'll bring that into perspective in a minute. The other point that I wanted to make for this discussion is that not all the copper iron sulfide stringers within a porphyry are a C vein. They are only a C vein if you can see a cross-cutting relationship that tells you that they happen after A and B veins, or after early halos and B veins and BMQ veins and all these vein paragenesis. So it's very common to have examples like this one on the left, where you have a lightly colored early halo with, when you are in the higher copper grade zones, the dissemination of copper sulfides inside the halo, they start to amalgamate and they make these anastomosing sulfide stringers that are formed with the halo, and they evolve as the halo is growing. So sometimes they are slightly younger, but they predate B veins. So these are not C veins. This is one example, maybe a bit better of a C vein, but now I have some doubts too. This is an A vein, 2 generations of A veins and an early halo, and you see this sulfide-rich veinlet with very little quartz cross-cutting these veins. Okay? But we don't have the cross-cutting relationship with the B generation. And this is probably a C vein, but after doing some more detailed work here, the little bit of quartz that we have here, it's similar to the A vein. It's also sugary. It's just that there's very little bit of it, and there's hydrothermal biotite and K feldspar in this vein. So it's very hard to know what's a real C vein without the cross-cutting relationships. I think this could be an A vein that it's just very rich in sulfide and doesn't have much quartz. Coming back to the early halos, they look like this. EDMs, they're called early dark micaceous. It's the first type of halo that was described at Butte. Very probably easier to recognize and more difficult to confuse with younger D veins because they're dark, but they're not the only type of halos, right? And the mineralogy of these halos, it's K feldspar with muscovite and some biotite and some trace faces like andalusite that we're gonna see in a minute. So it's an alteration selvage along a central suture. There's not a central quartz vein. If it is, it's younger or older. And the fluid goes through the central suture and makes this alteration selvage around. And in this case, we're seeing that the halo, it's cross-cutting A veins, and it's obliquely reopened by a B vein. There are early halos that are much lighter in color, and they're actually, I think, more abundant than EDMs. And to put some order in all this nomenclature, we call them pale green sericite or green gray sericite. It's been names that have been used before. They share the same characteristics of all early halos. They have K feldspar, muscovite, biotite. They are irregular in shape. They have these anastomosing sulfide center lines. And it's just that they have a little bit less of biotite or traces of biotite, and it really tricks your eye into looking at color. Okay, but the key thing here is that they are early. They're equally early to EDM halos. So we name all of these early halos rather than giving specific names. Even the ones that are very light in color and they have abundant muscovite and almost no biotite or traces of biotite, they have andalusite as a trace. And it's something that now that we have access to tools like this, it's a ChemScan or a TIMA image where you can see in very much detail the mineralogy of alteration. We're starting to see this more clearly. So this is also an assemblage that it's a pretty high temperature. And in this case, we use this name green-gray sericite for these lightly colored halos. And the ones that look more gray, they just have no biotite or just traces of biotite. The ones that look more green in this very light color version of halos, they have just a little bit more of biotite. And that's what gives the greenish color. It's not the abundance of chloride or smectite. But it's common to have intermediate overprints in all these halos. And that doesn't really change too much the color unless it's very intense. Very common to have hydrothermal biotite partially replaced by vermiculite, which gives hydrobiotite. So color is not a very good guide. The important thing is the timing and the mineralogy. So to put them all together, we can see from left to right, darker to intermediate colors to very light colors, and these subtypes of EDMs, PGS, and GGS. They all share the same mineralogy, as I was saying, K feldspar, muscovite, which is phengitic, with some biotite, and they have a shreddy texture, as we see in the wall rock too. And they're contained within a potassic or K-silicate alteration with more shreddy biotite. And what changes is the amount of biotite. So the lighter color, the less biotite they have. This is how it looks on a ChemScan. And if you see, this is K feldspar, the green is biotite, muscovite in this reddish color, and chalcopyrite. And when you go from EDM to pale green sericite, there's less biotite. And when you get to green-gray sericite, there are just traces of biotite. But the other mineralogy is still the same. The abundance of the biotite is related to the iron content of the wall rock. So the early halotype porphyry is emplaced in more mafic to intermediate wall rock, like Hakira and Butte, that they are in granodiorites. you tend to see more EDMs or pale green sericite type of halos because there's more iron and you favor the formation of biotite rather than muscovite. When you get to very felsic systems like Tacataca in Argentina, that it's hosted in a slightly, well, not slightly, in an older granite, there's not much iron in there, there's not much mafic content, and you only produce these very light color halos. And that's also related to the copper grade that you can host in the halos. So these, they struggle to go above 0.3 copper because there's not much iron to precipitate the sulfides. And these could have much higher grade. Nonetheless, the light color ones could make big and nice deposits too. The other controlling the mineralogy of the halos is the fluid to rock ratio. And that's why it's better to name them all early halos than to use these subtypes, because it's very common to have zonation in the halo. So the center area here where you have these sulfide center lines has more muscovite and biotite because there's more fluid going through here and there's more acidic conditions over time. The rock loses the buffering capacity, and as you go to the edges, you preserve more, you form more hydrothermal biotite and you preserve more biotite of the wall rock. So that's also very common. So bringing all that together, I talked about differences between the early halo porphyries and the A-vein porphyries, and there are many similarities. One of them is that the ore zone in both types is contained within the K-silicate alter zone, where there are porphyry dikes, and the copper ore zone is related to chutes where you have high density of A-veins or early halos or both, and they're both contained in the potassic zone. And then the other point that I mentioned before is that not all the quartz veins in a porphyry deposit are A or B veins. We have other generations of veins. Here are some examples of what we call banded molybdenite quartz veins, or BMQ. These were described very early on without that name. This is work by Nielsen in the 80s from the Santa Rita stock, where you can see that banding. And the characteristic thing they have is that you don't have the sugary texture that you have in A veins. You don't have the oscillatory banding and open space that you have in B veins. These occur in between A and B. You have more massive quartz, and you have molybdenite, especially in the edges in bands and some in the center, and no copper sulfides. Okay, and these are common mostly common in early halotype deposits because those are moly rich, but they're present in all porphyries. Even this is from Climax, so you have these are called railroad track moly or something like that, and it's the same morphology and at a very similar timing with alteration halos in those deposits too. So I will say that these moly porphyries are also of the early halo type family. Especially in South America, these were recognized as B veins before because they are commonly reopened by B veins. When you see this in cathodoluminescence, you see that the texture in the center line is different, and that's where you have the copper sulfides. So this is a reopening of a banded molybdenite quartz by a B vein. And actually, this was described by Gustafson and Hunt, where they recognize that deeper parts of the deposit have that, and that could be an independent vein generation. So it's important for the discussion because they have molybdenite, and when they're not reopened, they don't have copper. Then we have older veins that they predate A veins, and we call them deep quartz veins. They were previously named barren quartz vein at Butte, barren Stockworth veins at Bingham, barren A veins at Batu Hijau. We kind of avoid that name now because they don't have the sugary texture of A veins. They are not sinuous, they're not intermittent, they're more massive, milky, coarse grain. The inclusions of other minerals inside, like magnetite in this case, is also coarse grain, and they're closer in time to USTs and massive quartz and apletic dikes. So in this case, they're uplights that are cross-cut by deep quartz veins and uplights that cross-cut the quartz veins, which leads to these what we call vein dikes, which is deep quartz vein reopening uplights and uplights reopening deep quartz veins. So these are also important in the discussion because they don't have sulfides. And they are cross-cut by A veins and B veins and BMQ veins. So we can go back to the question of when copper is introduced and precipitated. And now in these two hypothesis frame, we can introduce this diversity. And it's important because, for example, in the early halos, we have a different perspective at this issue of the quartz timing because we don't have much quartz. And we see the sulfides in contact with other silicates that give us temperature information. And then in the ore zones in these deposits where you have the high-grade copper, you have barren quartz veins and veins with moly that don't have copper sulfides, and they're also affected by these multiple generations. So this is what we discussed in that paper published last year. We looked at 3 deposits, the porphyry deposit that captured this diversity from early halotypes to A veins. So we have Jaquira, Peru, in the Andahuaylas belt, probably form 8 to 10 kilometer depth. Typical early halotype, very similar to Butte. Batu Hijau in Indonesia, probably form around 2 kilometer depth. And something in between, which have both type of veins and shared characteristics of both types, which is Encuentro in the Centinela district of Chile. And the good thing of these 3 deposits is that they're relatively simple in terms of repetition of events and overprints. So they have a more simple progression of veins through time without too many overprints of different vein types and different alteration. And what we see in this deposit that they have been extensively logged from the perspective of looking at vein types, cross-cutting relationships, and the distribution of these veins in space is that there is an intimate relationship between potassic alteration, the abundance of quartz A veins in particular, or early halos, or both, and the copper ore. And the veins that are unambiguously C veins, they are volumetrically minor in the systems. So from this pure field point of view, there is a very strong correlation with these early veins, either A veins or early halos, and potassic alteration and the ore. And this has been described for deposits where this type of work has been done. And as I said before, all these deposits, they share characteristics. These 3 deposits have the key vein types and halos. They are observed in all 3 deposits. And the timing is virtually the same. So if we put together all the veining in these deposits in this schematic cartoon, it looks like that. That's wall rock. There's a porphyry dike, has a quartz phenocryst there. And then the first event, it's what we call this deep quartz vein, which are barren. They don't have sulfides. This is crosscut by A veins, sugary, plitic, discontinuous, irregular. Some are very sulfide rich. Some are not, and early halos, also with disseminated sulfides, sometimes having a lot of anastomosing sulfides inside the halos. Then these are cross-cut by the BMQ veins, which have molybdenite in these bands, but they don't have copper sulfides, and they cross-cut in space in the same areas of the deposit, right? And then these are in turn cross-cut by B veins, which have mostly copper sulfide, but they could have some moly in there too. And when we apply cathodoluminescence to these and try to see textures, and there's also quartz moly veins that cross-cut B veins in some deposits like Encuentro or El Teniente, for example. And all these veins that I mentioned until now, when we look at in cathodoluminescence, they have lucent Cl quartz. So all the variations of the brighter Cl types, and they're all stable with potassic alteration. The veins that follow, which are C veins with little quartz, but when you see quartz, it's not lucent anymore. It's what we call dull Cl quartz or dark Cl quartz. We see some indications of C veins being part of the central lines of some B veins. And then we have D veins, where there's absolutely no more lucent quartz at all. It's all dual Cl quartz types with abundant pyrite and muscovite, and only copper sulfides where these veins cross-cut older veins that have copper sulfides. So there's a big change from all the older veins from 1 to 6 here when you get into the C and D veins. And then when you look in detail in cathodoluminescence inside all the older lucent CL quartz, we see that these microfractures with dull CL quartz are everywhere. They cross-cut all the vein types. They are not only present in A veins, they are present in all these veins. So we think that each of these veins on the earlier lucent CL quartz generations are formed with their own distinct population of sulfides. Some have copper sulfides, some are barren, some have only molybdenite and don't have copper sulfides. And then the dull CL quartz that is late and much lower temperature percolates through microfractures that affect all these lucent CL quartz, and they become in contact with whatever minerals are included inside those vein generations. So no sulfides in deep quartz veins. It becomes in contact with copper sulfides in A veins, with moly and banded molybdenite quartz. So I'm going to show you some examples of what we've seen at this microanalysis scale. So this is a ChemScan image from an early halo. You see these are the feldspar, magmatic feldspar in the wall rock, and when you're inside the halo, they look like that. So they're completely replaced. And you can see a summary here of that replacement. It's K-feldspar, phengite, and biotite. And we discussed before that there's some andalusite in there too, and other phases. And what we see in terms of the sulfides is that chalcopyrite and bornite are usually completely enclosed in K-feldspar or in between shreddy muscovite, biotite, and K-feldspar, which shows that these sulfides are precipitated with these silicates during the formation of the early halos, and it has to happen at relatively high temperature, above that 450 degree. When we go to the A veins, we see this observation that has been seen and documented very well in every porphyry that has been studied with cathodoluminescence. That is that there's a lot of contact of copper sulfide in A veins with the darker dull CL quartz that it's younger. In some cases, the sulfides are completely included in this late quartz. But we also see that there are some sulfides that are mostly included or completely included in the older lucent quartz, which is the pink sugary texture quartz here. We see terminations of the younger quartz against the sulfide and stuff like that. And more interesting, we see that other minerals that are inside the A veins, like anhydrite and K-feldspar, they also are in contact with the dark CL quartz. And in some cases, the dark CL quartz completely surround this mineral. So we think that's evidence of sulfides, anhydrite, K-feldspar, they were all here, and then the dark CL quartz precipitated along those fractures. And this is maybe better explained if we see this in the context of cross-cutting relationships. So this schematic drawing is showing a deep quartz vein, a quartz phenocryst in a porphyry that is cross-cut by an A vein with copper sulfides and an early halo with sulfides. And there are no sulfides in the deep quartz veins and the quartz phenocryst. However, when you see it in cathodoluminescence, it's all almost equally cross-cut by this late dark CL quartz. So the only way to explain this cross-cutting relationship, because these occur in the same piece of core, in the same intercept, is that these sulfides were in the A veins and the early halos that cross-cut these veins that are barren, and then these late dark CL quartz come later. This is also reinforced if you see a younger time slot in the evolution of the system, where we have A veins and early halos here that are cross-cut by banded molybdenite quartz veins that only have moly, and that one is cross-cut by a B vein with moly and copper sulfides. And when you look at the cathodoluminescence, you see the sulfides in contact with no quartz in the early halos, biotite, K-feldspar, muscovite, in contact with dark CL and bright CL quartz in the A veins. And then you see the dark CL quartz in contact with molybdenite only in these banded molybdenite quartz veins, and both in contact with copper and moly in the B veins that are cross-cutting on the same space. So again, this is explained by having the sulfides as part of these veins before the dark CL quartz was introduced. And when you look at C veins and D veins, as Bertrand was showing nice pictures of these, you get into these very dark Cl and low titanium types of quartz. There's a lot of muscovite inclusions. And when you see cross-cutting relationships of a D vein cross-cutting an A vein, you see dark Cl quartz or dull Cl quartz cross-cutting lucent Cl quartz. So you see the same type of quartz and the same cross-cutting relationship that you see in the microfractures through all other A veins. So we think this suggests that this dull Cl quartzing microfractures, it's introduced close in time with the formation of C veins and D veins and the onset of sericitic alteration. So reconciling these two hypotheses in base of these observations, we propose that the bulk of the copper is introduced and precipitated with early halos or A veins, together with this lucent Cl quartz and instability with K-silicate alteration. And similarly, the bulk of moly, if there's enough moly there, it's introduced and precipitated in later events with banded molybdenite quartz veins or MQ veins. And then there's some more of both of those with B and C veins. And at the later stage, when the system it's dying, it's the first time when you go from potassic alteration to sericitic alteration that the system is going to sustain a prolonged cooling and it's not going to heat up anymore. And at that point is where everything cools down, and the high temperature quartz, as it cools down, it's going to contract. So there's a volume reduction on all the lucent Cl quartz generations. They're going to fracture to accommodate that volume reduction. And also that volume reduction overlaps in temperature with the field of retrograde solubility of quartz at low pressure. So any fluid migrating to these fractures that are produced by volume reduction will produce some dissolution and erosion, okay, further enhancing the permeability of these fractures. And we think that's why it's so common to observe in A veins, in particular, copper sulfides in contact with the dark Cl quartz. It's because the copper sulfides and quartz are crystals together, are grain boundaries discontinuities that are pre-existent before the volume reduction. So when the lucent Cl quartz cools down, some of this volume reduction is gonna be accommodated in those interfaces between crystals. So it's gonna be open space for that microfracture to expand and the fluid to precipitate there. And the same for the observation of dark Cl quartz with anhydride or K-feldspar or anything in those veins. So then what's different between early halo type porphyries and A vein type porphyries? Because the temperature of precipitation of the copper and the timing seems to be very similar, right? What we think is different is the pressure, and that's what ties back to the depth of formation. So this diagram is pressure against temperature, and you see these gray lines are the solubility of quartz. So what you see here is that if you start with a fluid at relatively low pressure, so an A vein type porphyry like Yerington or Batu-Hijau, when you release fluid from the cupola and it starts to cool down and upflow, it's gonna release pressure and cool down and precipitate copper, right? Because precipitate quartz, because it's gonna be cross-cutting these solubility fields of quartz. And when you arrive to that window of 450 to 550, when A veins and B veins are formed, you're still prograding and precipitating quartz. In the case of deep porphyries like Hakira or Butte, that fluid released at higher pressure is going to have a similar trajectory and precipitate quartz early on, probably where you produce these deep quartz veins in the center of the systems. But when you arrive to that window, 550, 450, you are in retrograde solubility of quartz. That more than real retrograde, I think it's just a bit of inhibition of quartz precipitation. And that favors the formation of the alteration halos and not precipitating veins. The other part of the story here is probably that the formation of acid from SO2 is pressure dependent. So in the high pressure systems, you produce more acid early on, and that's probably why you have muscovite with the early halos together with biotite and K-feldspar, and why there's no magnetite in these deep systems. So after talking for more than 40 minutes on timing and temperature, I'm going to put my exploration hat and think about how important it is to know the exact temperature of precipitation of copper for exploration. This relates to what Bertrand was saying of knowing the exact temperatures. And I think the answer is that it's not that important at all. But I think that the questions we need to ask to try to answer this are really important, and trying to answer those are really important. And that's understanding veining and alteration types and the timing and evolution of that in porphyries. And this is from a recent paper from Dick Silito and Pepe Perechot, and it highlights that mapping it's still really important in core logging, and mapping potassic alteration and quartz vein types. It's an essential exploration tool. So most of the high-grade copper in porphyries is associated with potassic alteration, and if it's not, it's in many cases it's because the potassic is masked by overprinting events. And the high density of quartz veins, it's also related to high-grade copper, right? And those quartz veins are in vast majority A veins. We can add to this story a little bit of complexity in terms of the deep quartz veins and B veins and that, and I'm going to expand a little bit on that. And that's why we need to have a nomenclature of the veins, that it's based not only mineralogy, but in cross-cutting relationships, because we need to have time to compare different generations. All these vein types, they are not, they have their own variation. So we need to have this timing to name the same a certain mineralogical group of variability. And that lets us compare across prospects, see what's similar and what's different between small porphyries and barren porphyries and economic porphyries and gigantic porphyries. And I think in some cases, if you're early on in exploration and you have copper hits, but they're not associated to the right type of vein, being A veins or early halos, there are chances you have a sub-economic porphyry more than an economic porphyry. This also takes some time and some effort. It's not easy if you're in an exploration project and your first meter of core gives you that. You will struggle to know if that's an early halo or a sericitic halo to a D vein, or Grayson alteration even, or intermediate Gillick overprints. And that's because we need to have those cross-cutting relationships. So this is something that needs to evolve as you do the exploration. And now we have access to these mineralogical tools like ChemScan and traditional petrography too. We need to make an effort to understand that mineralogy. So I'm gonna wrap up with a couple of slides on some thoughts for exploration too. I think one that it's related to everything that we've been discussing is that shallow and deep porphyries are explored differently, and A vein type porphyries are economic in copper and gold. They have little moly, and they have some characteristics besides having A veins, is that they're hosted in the highest grade is hosted in the oldest porphyries, and the mineralization is truncated against contacts with younger porphyries. So the effort of trying to find the early porphyry, it's really important and crucial. They're also magnetite and biotite rich, so geophysics, magnetics are gonna behave in one way. Early halo type porphyries are pretty different. They are copper moly rich and they have little gold. If gold is associated, it's present, is associated with bornite in the top of the barren core, so sort of and in the center of the deposit of the inverted cup shape zone. The mineralization is hosted usually in the wall rock, which could be the precursor batholith or a related stock or older volcanic or magmatic sedimentary rock. Breccias and high-grade copper breccias are common in these deposits too. And the porphyries that are closest in age to the formation of the deposit are very thin dikes and deep in the system. So there are not many truncations of mineralization by porphyry dikes. And there's not too much sense in finding the early porphyry in exploring an early halotype porphyry. They're also magnetite poor, and there's muscovite in the center of the deposit. So the geophysics, the magnetics of an early halotype porphyry is going to be the opposite of an A vein type. And then in terms of vein density, in A-vein type porphyries, the highest quartz vein density is coincident with the ore zone because of the A-veins, and it continues into the deep quartz vein zone in the barren core. Sometimes that zonation is disrupted because you have younger porphyries that are barren and veinless in the barren core. So in those cases, you end up, if you map quartz vein distribution, the most amount of quartz veins are in the ore. In the early halotype porphyries, the highest quartz vein density, it's coincident with the barren core below the ore, because the ore is associated with early halos on top of that barren core, and there's not much quartz vein. So this is an example from Hakira, comparing Hakira with Batu Hijau. That's sort of half of a shell of the copper shell in Hakira, 0.5 copper, early halos, A and B veins. There's a barren core here, and the highest density of these deep quartz veins are down there in the barren core. So if you have a prospect that it's outcropping at that depth and it's full of quartz veins, could be that it's it's too deep and there's not much copper in there. Whereas if it's an A vein type like Batu Hijau, there is a high abundance of A veins to deep quartz veins throughout the deposit and its roots, and you have that disruption by younger porphyries. And two more points in there is that muscovite is not a synonym of sericitic alteration anymore. We have muscovite in sericitic alteration associated with D veins, especially in the tops of the porphyries and periphery, or in D veins that cross-cut and are overimposed the K-silicate zone. But we have abundant, especially phengite in early halos, in the K-silicate zone. This was very early described by Cheney in the inside-out porphyry model in the 70s. So there's muscovite in there too, and we also have Grayson alteration that not every porphyry has it. It postdates the porphyry. It's related to the precursor batholith below, but you could have abundant muscovite even if the porphyry is eroded in the roots. Similar situation now with albite. Albite is not only forming sodic alteration, like this example here, we see some relict magmatic anorthite, some K-feldspar, and there's a wash of albite in this blue color that it's overprinting everything. And when you look at the whole rock, the whole rock, it's gaining sodium. But now that we have ChemScan, we're seeing albite in many places. This is our A veins with K-feldspar halos in orange, and related to those A veins and K-silicate alteration, where even the rock it's gaining potassium and losing sodium, we see albite. And this has been kind of misleading in interpretations. This albite, it's not added sodium, it's just during K-silicate alteration when the albite portion of anorthite recrystallize to K-feldspar to accommodate the added potassium. There is no more fit for sodium that was hosted in the anorthite, and some portions of that anorthite need to recrystallize into albite. So we need to be careful with that. So that's all. Thank you.
All right, thank you so much, Federico. Moving on to our next Q&A session. Go ahead and put your questions in the Q&A box if you haven't done so already. And I am going to bring the presentation back up. And if Dave and Bertrand would like to hop on, take it away.
Great. Thank you, Morgan. And thank you, Fede, for a beautifully illustrated presentation, really showcasing a whole range of different vein types from a number of porphyry systems. It was a real joy to see this Skinner Award-winning work. We are getting a number of questions populating the Q&A, so hopefully you're okay with answering some of these. The first is from Gilles Negoran, who has asked, how do you tell the difference between hydrothermal and magmatic K-feldspar in porphyry systems?
Well, it's hard to tell what's K feldspar just with a hand lens. You know, sometimes you have white K feldspar and it's not pink, and it could be confused with a magmatic. So it depends on what tools you have. If you can see these textures like you have in ChemScan or in petrography, you see that there are halos to A veins, for example, or replacements of other minerals. You see transformation of magmatic plagioclase into K feldspar and stuff like that. But yeah, it's tricky.
Yeah, it's unfortunate we can't do the HF etching and staining as commonly as we used to, because showing the textural context can be really helpful for understanding that. Martin Gonzalo Vallejos has said, thank you for the great presentation. With regards to molybdenite, is it only in the high temperature BMQ and QM veins, or might it also precipitate in C veins or other later veins? And do you see rhenium osmium dating agreeing with an early timing for moly in porphyry systems?
Yeah, well, it's only in these BMQ and QM veins. We haven't seen moly in younger veins than that. These QM generation sometimes are very thin molybdenite veins only. So if if you don't have enough cross-cutting relationships, it's hard to assign a time for that. But when we can do it, they are older than the C veins for sure. And then rhenium osmium, I think it's very good to date the hydrothermal system as a whole, but it's these events happen very, very quickly, so there's not enough resolution to separate it from the copper deposition, for example.
Yep. Yeah, thank you very much for that, Fede. Marissa Acosta has a question for you. If the microfractures are caused by thermal contraction of quartz during cooling, shouldn't all the microfractures by intergranular, long grain boundaries, and so on, rather than intragranular fracturing or vice versa? It's quite a complex question. So it looks like the late quartz is in both grain dissecting fractures and along grain boundaries. What's your thoughts on that?
Both grain dissecting fractures and along grain boundary. Yeah, we see it. I agree with that last phrase. We see it in both. We see in cross-cutting as microfractures at cross-cut and along grain boundaries. So you can trace a fracture that goes through the quartz vein, and when you get into a contact in between a pre-existent grain, doesn't have to be a sulfide or K feldspar and quartz. It's like the microfractures kind of bend and get into that boundary. I don't know if that answered the question, but yeah.
Yep. All right. Well, thank you. We're getting a couple of questions here, one from Virginia Gilliman and a similar question from Ajit Milliard regarding what happens with the vein variations when you go into different protoliths. So they were saying, well, you were showing, more felsic porphyries as hosts. What happens if you're in basalts or andesites? And you could take that out to what happens if you're in quartzites or so on. So does protolith impact on vein texture and composition?
Yeah. There is a huge control of wall rock. And I think it's easier to see in early halos, for example, because it's very dependent that replacement that you produce as an alteration selvage needs to replace something, right? So you see that variation more easily. So if there's a lot of mafic minerals and there's a lot of iron, you see better the early halos. There are more biotite, there's better high grade, there's more copper sulfide, etc. And if you go to an extreme case, like if you have quartzites, like in Hakira, the early halos, they disappear. When you cross from the granodiorite into the quartzite, there's nothing to react, and you don't see anything. And you don't precipitate much copper. There are some traces of copper sulfides, but there's not enough iron to precipitate the copper sulfides either, right? So, and then when you have the same type of transition with A veins, you will still precipitate quartz, but it will impact the amount of copper in the A vein too.
Great. Thank you for that, Fede. An anonymous attendee is asking a question about albertization. How do we tell the difference from addition of sodium to make albite versus destruction of the other feldspars? So is it sodium additive or sodium, loss of sodium and other components, but in different degrees, I guess the question is.
Yeah, well, I don't know, that's a tricky question. I think if there is addition of sodium, you will see it in the bulk chemistry. Right? If you compare from that bulk composition in a non-altered rock into something that have significant aldehyde added, you're gonna have more sodium.
Yep. All right. Jocelyn Pelletier says, amazing presentation, very generous, thank you. Is there any concentration of tellurium or selenium occurring at the level of the porphyry in either the A vein type or the early dark location vein type?
Yeah, well, there could be some. I don't really know of economic concentrations. Maybe you can add something to that, Dave.
Yeah, no, I think the tellurium tends to be concentrated at higher levels than the center of the porphyry. The selenium, the selenium might be a little enriched closer to the porphyry than tellurium. We have a question about the veins at the surface. How do you identify the different vein types when you're looking at in a weathered environment? D veins, AB veins, can you use moly and copper concentration to identify MQ veins on the oxidized surface? So basically, I think it's asking how do you see through the weathering profile to recognize the significance of different vein types?
It's very hard. Very hard. You need to be lucky to find the right outcrop that gives you some hints, and you identify something, and then you start guessing what you're seeing in the other outcrops. And of course, if you have some core of fresh rock to look before going to the oxidized environment, it's always better. But yeah, it's very tricky.
Yeah. Thanks, Fede. Thanks for that question, Diaz. Victor Torres says, great presentation, Fede. How does it correlate in the timing of copper precipitation when you've got tourmaline breccias, like we see at Rio Blanco, Los Bronces in Chile, versus vein paragenesis? Why do you think about where the brecciation fits in the paragenesis and when the bulk of the copper is introduced? He's also asking, can you remobilize the copper during phyllic alteration from the early Potassic?
I think you can, especially in breccias, but I don't have a good answer to that. I think breccias are complex, and what I've seen in some breccias is you see the gradation from potassic breccias to sericitic breccias in the same breccia pipe, right? So you see the progression from potassic to sericitic, but you don't have the veins to orientate yourself, so it's a bit trickier.
Yeah, no, certainly that happens at Rio Blanco, Los Bronces, and they're moments in time, Fede, so they're just a point in the paragenesis. Vic Chavillon has asked about the degree of crystallinity of sulfides with regard to elevation. It's also asking about pneumatolytic mineralization in the system.
I have no idea how to answer that.
Nor do I. I've never thought about degree of crystallinity of the sulfides. Thought about it from a white mica perspective, for sure.
Yeah, what I can say of that is that the sulfides that we are observing now, they have recrystallized at low temperature. So you cannot be sure how accurate is that reflecting what precipitated originally.
Yeah, thanks for that. Nathan Carey is asking, with regard to the deep muscovite alteration in the grisons, is it always laid in the paragenesis, and does it overprint or replace the potassic copper-rich zone?
Yeah, well, the ones I've seen, yes, it's seems to be happening after the porphyry has died. So it's not fluid coming from the porphyry cupula. It's sort of the leftover fluid from the precursor batholith that invades these areas. So in that sense, it's younger than the porphyry, but it can invade the roots of the potassic zone.
Yeah. Rene Gonzalez says, great presentation, Fede. he's observed in many porphyry and skarn deposits, there's a really good correlation of gold and bornite with the higher gold content compared to the systems where you're getting gold and chalcopyrite. Do you have any thoughts on why that's the case?
Yeah. Well, I don't know why, but I think it relates to what Bertrand was showing with the temperature. Bornite can fit more gold in its structure than chalcopyrite. So in the early halo systems, when there's abundant more bornite, you have a spike in gold, and if you're lowering the abundance of bornite, when the bornite disappears, the gold disappears. But yeah, probably related to temperature there.
All right. An anonymous attendee is commenting on the sulfide events of chalcopyrite and bornite. I think he's sort of referring to the sulfide-only veins that have been documented from places like Grasberg and Oyu Tolgoi, and I guess this goes into the paint veins as well at Badahijo and the like. Are they, he asserts, they're major contributors to the grade of these deposits. Are they C vein variants, and where do they fit in your model?
Yeah, there could be C veins variants. Where you can map them and see that there are clearly post-dating B veins, and they're only cross-cut by D veins. They're only locally abundant in some areas, and it looks in Badahijo there's one area that looks like that, and it gives the impression that it's like a local remobilization of the grade. There's not a big difference with the grade in other areas, right? And the problem with that is that you usually don't see, even in those places where C veins that are of the proper time are abundant, they're always overprinting these potassic zones with A veins. You don't find these shoots of C veins in sericitic stuff that are not overprinting the potassic zone. So I think it has to be related to remobilization.
Sure. Okay. I can see Morgan's popped up on the screen. Morgan, would you like to say something?
Yes, thank you. We have time for one more question.
All right. So our last question is from an anonymous attendee. How do the cross-cutting relationships between copper and gold and moly-bearing veins and the pressure temperature evolution path you've recognised reconcile with the observations of typical copper-gold porphyries, where we see a gold copper-rich core and a moly annulus around the gold copper-rich zone? And the question's being asked because they've done some fluid inclusion work suggesting that redox and pH changes might be affecting those temporal and spatial distributions of gold, copper, and moly.
Yeah, I don't know. It's difficult to compare those systems, right? Because in one you're looking at high grade moly in discrete type of veins. I think in space they are kind of associated in the same area. In many cases, the moly zone kind of includes the copper zone, and but in terms of timing, even in the gold-rich porphyries, I think the veins that have a little bit of moly, even if they're not very abundant, they are at the same timing, and the moly is slightly peripheral. But it's difficult to compare when you have such a big variation of grade.
Great, thanks, Fede. I think we'll hand back over to Morgan now. Thank you, Morgan.
Right.
Thank you very much. Thank you to everybody for that Q&A session. That was great. And thank you again to Federico for that presentation. All right, I want to talk about some upcoming events that we have. We have a 2-day course that's an in-person course, and well, I thought I fixed that, but it looks like I didn't. Hold on just a second. Okay. Yes, we have an Orogenic Gold course coming up. That one's in person, 2 days at the University of Zimbabwe. We have a virtual drill, deal, drop course. That one is coming up online. And then we have a 1-day ore deposit at the nanoscale course, and that will be at the University of Toronto. So these are all really exciting upcoming instructional events that we have from SEG. Also, I want to call everyone's attention, podcast lovers, to the SEG podcast, Discovery to Recovery. I apologize again for that slide. This is a great podcast from SEG student chapters. We also have a podcast competition open for submissions. We're inviting student chapters to produce a 12-minute interview style audio podcast, tell your geoscience stories from the world of ore deposits. And teams have a chance to win thousands of dollars in prizes and potentially be featured on an episode of Discovery to Recovery. So the deadline for submissions is March 17th. And you can visit the SEG website for more details on that. Also, very exciting, our next conference, SEG 25, is in Brisbane, Australia, and that will be September 26th through 29th of this year. Super exciting. This will be an incredible platform to showcase the latest research, industry, discoveries, and relevant discussions that impact our membership the most. The conference will feature pre- and post-conference field trips and workshops, a full student and early career professional development day, as well as student poster presentations and speed talks. We hope that you consider joining us, and please stay tuned for more conference updates in February. We'll announce the abstract submission opening and registration opening next month. Again, thank you so much for attending this webinar. An extra special thank you to all of our members out there. We really appreciate it. We hope that you found it informative and engaging. We do have a survey. That survey will appear for you once the webinar has ended, and we'd really appreciate your feedback. Thank you all so very much.